Hello students, in this video we will see a linear differential equation with constant coefficients. We will see its general form and I will introduce you to its general solution. We will see how to find its general solution. So the general form of nth order linear differential equation with constant coefficients is this: d n y upon dx raised to n. This is the nth order derivative of y with respect to x plus a1 times n minus 1th order of derivative of y with respect to x and so on, plus a n y is equal to f of x. Here all these ai's are constants and therefore we call this as differential equation with constant coefficients, and its general solution contains exactly n arbitrary constants. Okay, now we know that a linear differential equation of first order is, so this is a general form of linear differential equation of first order. Remember, this is not linear differential equation of first order with constant coefficients, because the coefficient of y is a p of x. This is a function of x. This can be constant also, but in general case it is a function of x, so we cannot say this as a special case of this differential equation. Okay, but if this p of x is a constant, then it is a special case of this differential equation. Okay, so right now we have this differential equation and we know how to find its solution. First step is we find its integrating factor, which is e raised to integration of p of x dx, and the general solution is y into integrating factor is equal to integration of integrating factor into q of x dx plus c, where c is the arbitrary constant. And because this is a first order linear differential equation, its solution will contain, its general solution will contain exactly one arbitrary constant. Okay, so this is about first order differential equation. Now let us take one example of this. So we have this differential equation dy by dx plus 2 of y is equal to x. Let us call this as equation number 1. Now see here, this is a differential equation with constant coefficient, so it is a special case of our general form. Alright, so how will you solve it? So we'll first find its integrating factor, which is e raised to 2x, and then general solution will be y into integrating factor, which is e raised to 2x, is equal to integration of e raised to 2x into x dx plus c. Now after integration we get this, and when we divide both the sides by e raised to 2x, we got y is equal to x by 2 minus 1 by 4 plus c into e raised to minus 2x. So this is a general solution of this differential equation. Now see here, this differential equation has two parts. One is this x by 2 minus 1 by 4, and the second is c into e raised to minus 2x. So one part which is without arbitrary constant and the second one which contains arbitrary constants. Okay, now let's see how these two parts are related with this differential equation. See, our general solution is a sum of these two parts. Okay, now let's start with the first part, the one which is without arbitrary constant. Okay, now apply d by dx on this, we get 1 by 2. When we multiply this by 2, we got x minus 1 by 2. Let's add these two equations. So we get this d by dx of x by 2 minus 1 by 4 plus 2 times x by 2 minus 1 by 4 is x, which gives us this equation. Okay, now what is the similarity between this and the first differential equation? Can you observe any similarity here? So here we can call this x by 2 minus 1 by 4 as a solution of this differential equation 1. Remember, we are calling this as a solution, and this one which is given here is a general solution. See, it is a solution in the sense it satisfies the given differential equation. When you replace y by x by 2 minus 1 by 4, it satisfies this equation, and therefore we call this as a solution of given differential equation. Okay, so the first part satisfies our differential equation. Now let's come to second part, c into e raised to minus 2x. We'll apply same method. D by dx of c into e raised to minus 2x is minus 2c e raised to minus 2x. Then 2 times c into e raised to minus 2x is 2c e raised to minus 2x. Next we'll add these two and we are getting 0. Now see, here we are not getting x, we are getting 0 here. In the previous case we got x. So what this tells us? This tells us that c into e raised to minus 2x satisfies this differential equation, d by dx plus 2y is equal to 0. Okay, now what is the relation between this differential equation and the original differential equation? So here the right hand side is 0. Alright, in the original differential equation we have this f of x function of x. Now it is 0 here. So the second part, c into e raised to minus 2x, is basically a solution of the homogeneous part of the differential equation. When this f of x is equal to 0, we call this as a homogeneous differential equation. Okay, so this is a solution of homogeneous part, and the general solution is sum of these two. General solution is a sum of this one which is without arbitrary constant, which is a solution of our differential equation, and the other one which contains arbitrary constants, which is a solution of homogeneous differential equation. Okay, so here this x by 2 minus 1 by 4, we call that as a particular solution because it satisfies the differential equation. It satisfies given differential equation. We call that as a yp. And the second one we call that as complementary function, yc, c into e raised to minus 2x. So this is our yc. And complementary function contains the arbitrary constant. Okay, so general solution y is basically yc plus yp, sum of complementary function and particular solution, or we call that as particular integral also. So this is about first order linear differential equation. So this is how we find solution of first order linear differential equation. Same technique we will use to find solution of this nth order linear differential equation. Okay, so this is our nth order linear differential equation with constant coefficients. So what we'll do here, so first step is we will find its complementary function yc. How to find complementary function? It is a solution of homogeneous part of differential equation. So this is a homogeneous part and its solution which contains n arbitrary constants, we call that as complementary function. And then particular integral yp, so this is solution of given differential equation. Okay, so later on we'll see how to find this yc and yp. So right now yc is what? It is a complementary function, it is a solution of homogeneous part, and yp, it is a solution of given differential equation, and the general solution is complementary function plus particular integral, that is y is equal to yc plus yp. So this is how we find general solution. Okay, it is a sum of two solutions, one complementary function, that is a solution of homogeneous part, and one particular integral, that is a solution of given differential equation. In next videos we will see how to find these yc's and yp. Thank you.